Hello students. So here we are today. Uh, we are going to learn a different thing today. The thing related to this electric potential. Okay. So today's topic is electric potential energy. Okay. So let me write today's topic. What is today's topic? Electric potential energy. In the previous classes, you learned about electric potential difference, the relation of electric potential difference with electric field. You learned about equipotential surfaces, and you learned about the relative distance between those equipotential surfaces when the field is stronger, and you also learnt about the relative distance between those equipotential surfaces when the field is weaker. Okay, so today we shall be learning about electric potential energy. It is a very good concept, it is a simple concept, so it is very easy to remember by. Okay, so electric potential energy. So what is electric potential energy? Okay, so you have a system of charges. Okay, you have some system of charges like q1, q2, q3, q4, q5, anything. Okay, this is q1, this is q2, this is q3, and so on, like q, and you have a system of charges. Okay, now if I consider these two systems, if I consider these two systems and ignore that the charges, the other charges do not exist at that part of the space. Okay, so if they are infinitely distance apart, if the distance between them is infinite, if the distance between them is infinite, then if we move q1 or q2, okay, we are saying that this distance is infinite. Okay, not at this place, we are talking about all of the universe, that the distance between them is infinite. So if you move one charge, then it is not going to be affected by the other. Okay, if you move the charge q1, you need not do any work, you need not do any work if it is at infinity from charge q2, and if you move this charge, you need not do any work. Now the fact is that you are going to bring those charges closer, you are going to bring those charges closer, like this is q1 and this is q2, we are bringing it. Okay, you are bringing q2 from infinity towards q1. So at some closer points, or at some finite distance, this charge is going, since these are both positive charges, it has an electric field that goes radially outward. It is going to get, or the electric field, or it, this charge is going to feel that electric field repulsion. This charge is going to feel that electric field repulsion because they both are positive charges. Then if we are going to bring this charge any more closer without disturbing the place of q1, the location of q1, then we will see that we have to do work against the electrostatic force of q1 on q2. Okay, so understand this concept very carefully, or listen to this concept very carefully, that when they were infinite distance apart, you need not do any work to move q2 or q1. Now you are setting q1 to be fixed and bringing q2 from infinity towards q1 against electrostatic forces. That means you are going to do some work, you are going to do some work, and that work is stored as the electric potential energy. That work is stored as the electric potential energy. Okay, so why that work is stored as the electric potential energy? Because electrostatic force or electrostatic energy is a conservative energy, or electrostatic force is a conservative force, so that energy is not like energy does not disappear from anywhere at that point. So that work done, that the work you have done on bringing q2 towards q1, closer towards q1, that energy has changed or has converted itself into the electric potential energy of this system. So you can actually understand that the electric potential energy is due to the virtue of their position, or each virtue of their position, of the position of their charges. Okay, so what is electric potential energy? So you can actually give the simple definition that it is the energy that is required in assembling. In assembling, you are assembling means you are fitting some charges at a finite portion of the space. So it is the energy that is required in assembling a system of charges. Now you have brought Q2, now you bring in Q3. That means you are going to bring Q3, or you are going to do work on Q3 such that it is able to come against the electrostatic repulsion of these two charges on Q3. Okay, so that energy also is also stored as the electric potential energy. So what was the definition, or what is the definition of electric potential energy? Listen to me carefully. So what is that? It is the energy that is required to assemble a system of charges by bringing them in from infinity. You have a numerous number of charges settled at infinity such that they do not interfere with each other, and you are going to bring them from infinity and make them a group of charge under a finite portion of the space. Then you will be needing to do some work, you will be needing some energy, and that energy is the electric potential energy of that system. Okay, and that energy is converted into the electric potential energy of that system. So write the definition. So what is the definition of electric potential energy? It is quite a simple definition. So what is that? Electric potential energy, it is the, follow me, it is the energy that is required, to assemble a system. So you are going to form a system of charges that is required to assemble a system of charges by bringing them closer from infinity. So they were actually at infinity, or the distance between them was infinite, and you tried to, or you brought those two charges together by fixing one, or you bring in either of them. So you work against that electrostatic repulsion, and that work is stored as the electric potential energy of that system. So it is actually the energy that is due to the location of the charges. It is actually the energy, it is actually the energy due to the location of the charges, locations of those charges. Okay, so it is electric potential energy. It is denoted by U, sometime E. No, E is electric field. Okay, so it is denoted by U basically. It is denoted by U. You can write that. It is denoted by U. So we are going to calculate the electric potential energy for a system of two charges first, and then we are going to proceed further by bringing in a third charge, a fourth charge, and continue up to that when we are going to find the formula for or for the general formula for a system of charges. Okay, so if we are going to find the formula, that means we already have Q1. We already have Q1. We have Q1. Okay. We already have Q1. So if you have Q1, was there any field before bringing Q1? There was no field before bringing Q1. Okay. So you need not do any work. You need not do any work in bringing Q1 from infinity towards a smaller portion of the space. Okay, you need not do any work. Now you have, if it is a point P, let it be P1, and another point there is P2. So the distance between them is R1 2. Let the distance between them is R1 2, and the second charge Q2 is infinite distance apart. Okay, it is infinite distance apart, and it is brought up to this point. It is brought up to this point such that the electrostatic repulsion Q2 fields due to Q1 is significant. Okay, now when you bring this charge from this point to this point, you do some work. You do some work. So what is that work? Now we are going to calculate the potential of Q1 at this point. So potential of Q1 at P2, what is that potential? V is equal to, you already know, 1 upon 4 pi epsilon naught Q1 by R12. This is the value of the potential at P2 due to Q1. Now since the potential is this, you bring Q2 from infinity to this point, then you have to do some work. According to the first definition, when we were starting electric potential, we already had that definition that the work done is W is equal to Q2 times this potential. Q2 times the potential at point P2. Okay. Since the other point is at infinity and the potential at infinity is 0. So now you put those formula, Q2 multiplied V. What is V? 1 upon 4 pi epsilon naught Q1 by R12. These are the subscript. So this work done is actually equal to that potential energy U. So what is U? 1 upon 4 pi epsilon naught Q1 Q2 by R12. This is the general formula for a system of two charges. This is the general formula for a system of two charges. If you have two charges and you are going to calculate the electric potential energy for the system of these two charges, then you will be using this formula. This is the required formula. This is the required formula. You can number it. So what is U? U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. So this is actually W2. This is actually W2. Why W2? Because if you have done work in bringing Q1, that would be W1. That would be W1 if there is any field and you have worked against this electrostatic force of repulsion to bring in Q1 from infinity towards this point, then you should be doing W1 work. So this U is actually equal to W1 plus W2, and W2 is this thing, and W2 is this thing. So this is the electric potential energy of the system of two charges. So the important thing is this. So if you have two charges and you are going to calculate the electric potential energy for that system of two charges, and you know the two charges Q1 and Q2 and the distance between them, you can actually use this formula. Okay, now I am going to write this formula in the sideways. Okay, I am going to write the formulas in the sideways. So what is U? It is 1 upon 4 pi epsilon naught Q1 Q2 upon R12. Q1 Q2 upon R12. Okay, this is the formula. Now we are going to bring in Now Q2 is reached here, has reached here, so we need not denote Q2 at that point. Now we are going to bring in a third charge. Now we are going to bring in a third charge Q3 from infinity to a point. Let that point be P3. Now we bring Q3 from infinity to a point P3. Okay, that point is P3. If it is R12, if this distance is R12, then this distance is R13 and this distance is R23 or 32, whatever you can denote it. Okay. Now Q3, we bring in Q3 by actually doing some work against the electrostatic repulsion of Q1 and as well Q2 as well. Okay, we have brought out Q3 from infinity towards this point by doing work against the electrostatic repulsion of Q1 against Q3 and Q2 against Q3 as well. That means we are going to calculate the work done. So actually the work done in bringing this thing would get added by to the work done by bringing these things and these things apart or closer. So let us now calculate the work done by bringing these things. So for Q2 Q3, what would be that work done? So let that be U23 is equal to 1 upon 4 pi epsilon naught Q2 Q3 by R23. Q2 Q3 by R23. Okay. Similarly, when you bring in Q3, you have to do work against the electrostatic repulsion of Q1 on Q3. That is U13 is equal to 1 upon 4 pi epsilon naught Q3 Q1 by R13. So you already had the work done or the electric potential energy of the system of Q1 and Q2. Now you added Q3. So the total electric potential energy would be 1 upon 4 pi epsilon naught. You can actually take 1 upon 4 pi epsilon naught common and then add these things. So you had actually this thing first, Q1 Q2 upon R12 plus then Q2 Q3 upon R23 plus Q3 Q1 upon R13. This is your general formula for a system of 3 charges. This is your general formula for a system of 3 charges. That means you need to do this much of work to hold the system of 3 charges so that they don't go apart from each other. Now if you have hold their position in steady in the steady positions, now if you just leave them that such that there are no external force except these forces, these electrostatic forces, then they are going to set themselves apart from each other. So I think you have got the formula for the electric potential energy for a system of 3 charges. Now we shall be drawing in the formula for the general formula for a given system of charges. Okay. So I think this is disturbing thing from infinity to point P3. So what is the general formula? So if I may, that you have written all of these things. So the general formula would be, you do not require these things. So the general formula is 1 upon 4 pi epsilon naught summation all pairs. Okay, all pairs. This is Q1, Q2 are pairs, Q2, Q3 are pairs, Q1, Q3 are pairs. If there are so many or more than 3 pairs or more than 4 pairs or many pairs, I'm not giving just a smaller number. So what should be there? Qi Qj by Rij. This is the value of electric potential energy of a given system of charges. This is the answer. This is your answer. So you have actually derived the electric potential energy for a system of two charges, and then we derived the electric potential energy for a system of three charges, and now we have actually given you the electric potential energy for a system of n charges, where you consider everything or every pairs. Okay, you consider every pair and then calculate the relative electric potential energy of those pairs individually and then add them. So in general you will be given two such charges or three such charges or four such charges, and you will be asked to calculate the electric potential energy of that system, or what is the energy required to hold those charges at those points. Actually that type of question you are going to be asked in the exams. So what is that question? That question is, so if it is a square, okay, the question is, if a square is given q1 q2 q3 q4 are the charges at the corner of the square, all are positive charges, or any negative charge be also given if given. So you will be asked to calculate the electric potential energy required. If all of these are positive charges, then they would be trying to go apart from one another. So what is asked, it is asked actually that what is the or what is the energy required to hold these things together, so to answer that, you shall be calculating the electric potential energy between this pair, and between this pair, and other two pairs also remain. This and this also form a pair, and this also form a pair, this pair, and actually take care that you do not repeat them. The electric potential energy between in this pair or q1 q2 is the same as q2 and q1, and you would not be like to repeat them. So how many such pairs are there? q1 q2 is a pair, q2 q3 is a pair, q3 q4 is a pair, q4 q1 is also a pair, and apart from those pairs we have also diagonal pairs, that is q1 and q3 and q2 and q4. So I consider I am going to stop the lecture at this point of time. If you have any doubts regarding this lecture or any previous lecture, you can actually put a comment on that video, and I have given you the contact details in the description box. You can actually contact me there for any numerical, if you have any problems regarding numericals in physics in plus 2 or plus 2 first year or plus 2 second year. CBSE, both CBSE, ICSE and state boards students are also welcome. So up until then, take care, keep practicing and share it with your friends, like our videos and subscribe us. Thank you all, see you.